to this. Welcome back to the next session of this interactive live session of the NPTEL course Applied Linear Algebra for Signal Processing, Data Analytics, and Machine Learning. So, the instructor of this course is Professor Aditya K. Jagannathan from IIT Kanpur. So, again, as usual, I'll give a brief introduction about myself before I begin, for the sake of all of you to know a bit about myself. So, my name is Yashvanth, and I'm currently a Ph.D. research scholar under the PMRF fellowship, and I'm affiliated with the Department of ECE at IISc Bangalore. So, I'm advised by Professor Chandra R. Murthy with the Department of ECE. My broad research, excuse me, my broad research interests lie in statistical signal processing, wireless communications, and communication systems in general. While my current research focus is on developing algorithms and devising techniques and designing systems which have intelligent reflecting surfaces for 5G and beyond wireless communications. So you can feel free to contact me in this email ID, and you can also know more about myself if you just navigate through this link that you see here. So today, the topics that we will be covering will be focusing on determinant of matrices and system of linear equations, which really, are the topics that Professor had covered in the second week of lectures. So part one of this session will be to quickly summarize this week's lecture. Okay. So the first topic is determinant of matrix. Okay, A. Okay, it's denoted by. Let me see if I can. What is this? Okay, so it's denoted by this. The two bars on the left and right side of the matrix, or you can also call it as det of A. Both are synonymous, and it's a function that maps any square matrix to a scalar number. Note that determinant is defined only for a square matrix. For example, if I consider matrix as shown here, which has m rows and m columns, so it's a matrix of m by m size, then you can define the determinant as something like this. It's summation over I equal to 1 to m aij cij. For you can take for any j, or you can define it as sum over j equal to 1 to m aij cij for any I, where cij is called the cofactor of the corresponding entry aij. It is defined as this particular function, which goes as minus 1 power I plus j times mij, where mij in turn is called as a minor. Let me tell that here. It's called the minor of entry aij. Can again anyone confirm if you're able to hear me and see my edits on the screen?
Yes, sir. We can hear you, sir.
Sure, fine. Thanks. So mij is called the determinant of the reduced matrix, which is obtained by removing row I and column j. So having set up the definition, let me quickly go over an example of how to compute the determinant of a matrix. For example, let me consider matrix A equal to 1, 2, 3, 4, 5, 6, 7, 8, and 9. Then one way to compute the determinant is by expanding the determinant along the first row. What does it mean? That means I'm going to use this particular expression, that is for, for some I. I'm going to use this particular expression, the second expression here, and set I equal to 1. That means I'm going to focus on the first row, and I'm going to vary my j value. So if you write down the expression for that, you're going to get like this. Det of A equal to A11 C11 plus A12 C12 plus A13 C13. Okay. So that is, it now what is A11? Just 1. A12 is 2 and A13 is 3. So collecting all of them, you get the corresponding coefficients. Now how to get C11? That is nothing but minus 1 power 1 plus 1 times the M11, which is same as M11 itself. C12 is given by minus 1 power 2 plus 1 M12, which is nothing but minus M12. And C13 is minus 1 power 3 plus 1, which is same times M13, which is same as M13. Now substituting these values for C11, through C13 in the above expression, you get this as a final expression. Okay. So now what remains is to compute M11, M12, and M13. Okay. So what is M11? M11 is a determinant obtained by deleting the first row in the first column. So this is really the first column, and this is really the first row. So delete it. So the remaining matrix is this one, and take the determinant of that matrix. So 5, 6, 8, 9. If you do the determinant 5 times 9 minus 6 times 8, which is 45 minus 48 equal to minus 3. Similarly, if I take M12, it's obtained by deleting the first row and the second column. So remaining is 4, 7, 6, 9. You should write them in the same order as shown here. 4, 6, 7, 9. And expanding it 4 times 9 minus 6 and 7 equals minus 6. Similarly, M13 is given by deleting the first row and deleting the third column. And the remaining matrix is 4, 5, 7, 8. Write it as it is here. And it expands determinants 4 times 8 minus 7 times 5 equal to minus 3. And now substitute these values for M11, M12, and M13 in this expression det of A. And by substituting, you can show the determinant becomes 0. It's just a coincidence that the determinant is 0, but in general, determinant can be any scalar value. It can be even a complex value. If the matrix is complex, as well, the determinant can be complex. Okay. So this is really about the determinant. Now, the second concept that was alluded by professor was the inverse of the matrix. So A inverse, there is a notation for inverse, A power minus 1. That is a notation for inverse, is defined as 1 by determinant of A times the adjoint of the matrix A. Okay, where adjoint of the matrix A is nothing but the cofactor matrix. The transpose is a cofactor matrix, where the ijth element of the matrix cofactor matrix C is given by the cofactor of the aij element of the matrix A. Okay, so this, I think, a professor had done an elaborate proof or an elaborate example rather in the class to basically explain what it means. And the next, some few results are, if 1 minute. Just 1 minute. Okay, I just changed the recording device. Okay. Okay. So these are some of the few results. So if the determinant of a matrix is 0, then the inverse of the matrix does not exist. Okay. In that case, the matrix is said to be a singular matrix. Now, if the inverse of the matrix exists, okay, then the inverse is always unique. It's not possible for a matrix to have two different inverses. The inverse of a matrix is always unique, and the inverse will exist only if the determinant is not 0. Or in other words, if the determinant is 0, the inverse cannot exist. Okay. The next very important use case of matrices is in obtaining the solution to a system of linear equations. Okay. So what is linear equation? Means that all the variables, for example, x1, x2, and so on till, sorry, okay, x2, x1, x2, and so on till xn, all these are the variables that we want to determine, and all of them appear linearly. That is, they don't come as a function like x square. X square is, for example, a non-linear function. X is a linear function, so they appear as a linear factor. Okay, and every such variable is multiplied by a corresponding coefficient a11, a12, and so on till a1n. Okay, so what is system of such linear equations? You have m such equations. So all these m equations constitute the system of linear equations. Okay, there are m equations in n unknowns. Okay, the objective is given the values of all the aij, and the values of corresponding y1, y2, and so on till ym. What are the values of x1, x2, and so on till xn, such that all the system of linear equations holds true. Okay, so these are the system of linear equations with n variables and m equations. The goal is, given the observation vector y and the values aij, solve for the vector x. You can really write these system of linear equations as in matrix vector form as follows. So basically collect all the values a11, a12, and so on till a1n and make that as a first column of the matrix A. From the second equation, collect all the coefficients of the variables and stack them as a second row of the matrix A. And similarly, you take the last column's coefficients and then stack them as the last row of the matrix A. And write down the matrix, the vector x as the vector of all corresponding unknowns. And then the vector of y is the corresponding all observations. Then this particular set of linear equations can be represented in compact form as this matrix vector product form, ax equal to y, where A is called, A is a matrix in m by n dimension. That is, A is a m by n matrix, where m is the number of equations and n is the number of unknowns. X is a vector in C to the n, and y is a vector in C to the m. Okay. Now, if you want to solve for vector x, just take the inverse of A and post multiply it by y. That is, A inverse y will give you the solution to this system of linear equations. But note that this particular approach will work only if A is invertible. If A is not invertible, then we need to, this particular solution will not be the unique solution. We will explore these aspects in detail in today's session. Now, one application of such kind of system of linear equations will arise in MIMO wireless communications, which even professor had explained in the course. So you have NT antennas at the transmitter and you have NR antennas at the receiver. Okay, so I will index all the antennas by 1, 2, and so on till NT, and the receive antennas as 1, 2, and so on till NR. Now, there is a channel between every antenna in the transmitter with every antenna at the receiver. Okay, for example, the channel between the first antenna at the transmitter and the first antenna at the receiver is called H11. The channel between the first antenna at the transmitter and second antenna at the receiver is called H21. Okay, the convention is that Hij means it's a channel between ith receive antenna and jth transmit antenna. So this is the convention that I'm going to follow. The first index will represent what is the index, what is the index of the receive antenna, receive antennas, and the second index represents the index of the transmit antennas. Okay, for example, the channel between the second transmit antenna and the first receive antenna, this channel is denoted as H12. And similarly, the channel between the nth transmit antenna and nth receive antenna is represented by HNRNT. Okay, I hope this is clear. Let me check. Am I still there? Okay. So now what we can do is we can stack we can write the input vector x and output received signal y in this particular relation. Okay, this is a received signal and this is a transmitted signal. In between, there's a channel matrix, which is really of the form y equal to ax. Okay, so this can be written as y, this can be written as a, and this is x. Okay, so y equal to, here a is called h. I'm just calling it as h because all the entries are denoted as in terms of h. So y is an nr cross 1 vector, h is a nr cross nt matrix, and x is a nt cross 1 vector. Okay, now if after receiving the symbol or signal at the receiver, if I want to estimate what the transmitted signal is, I just need to basically take the inverse of the matrix H and bring it pre-multiply the inverse matrix on both sides, for example, you will get this equation. So this is also called as a zero forcing receiver in the wireless communication literature. Again, this H inverse, whether it's invertible or not, is something that is still uncertain. But nonetheless, this is an example of how to cast real-time, engineering applications as one system of linear equations. Okay. So again, a crucial question is: suppose if A inverse is not defined, how to solve for system of linear equations? Okay. We will explore this in detail in today's session. And we professor had also alluded to applications of the linear system of equations in electrical circuits, especially by applying the Kirchhoff's voltage and current laws. He obtained a set of linear equations, and you can solve for the currents in every branch by casting the equations in the form Ax equal to B form. Okay. Another application which the professor had described was in applications to graph networks, where basically he defined something called the adjacency matrix, which basically represents the connection status between any two nodes in the graph. Whenever there is a link between the ith node and the jth node, then the corresponding Aij entry in the matrix adjacency matrix will become 1, else it becomes 0. Okay. Another application was in representing a directed graph. For example, it's possible that you will have a link from the jth node to the ith node, but the converse, the reverse, ith node to jth node, the link may not be present. So in order to capture all these, all these systems modeling, you can represent this by a very compact form, by a matrix, by a vector matrix relationship, just as a linear system of linear equations. Okay. And the next concept, in fact, this is the towards the last lecture on the last of the second week, the professor alluded to the concept of null space of the matrix A. So let me consider matrix A, which is of dimension m by n, right? Which means it has m rows and n columns. Then what is null space of a matrix? So it is a set of all vectors x in C to the n. Note that this is a set of all vectors which are n dimensional, which is equal to number of columns, right? So all set of all n dimensional vector x such that Ax equal to a null vector. See, it's a zero vector, not a zero scalar. It's a vector. Okay, that is, you take all collection of vectors x such that Ax will become a null vector. Collection of such x's is said to form the null space of the matrix A. Or in mathematical notation, it's denoted as n of A, just as how column space was denoted by C of A. Null space is denoted by n of A is equal to set of all vectors x in C to the n such that Ax equal to a zero vector. Okay. So can anyone tell me what is the dimension of this vector? What is the dimension of zero vector here? Is it an m length vector or n length vector?
N length and cross 1.
It's m, right? Because A is m by n and x is n by 1. So total is m by 1. So this vector, zero vector is an m by 1 vector. This x vector is an n by 1 vector. And this matrix is an m by n matrix. Is that okay?
Right.
Yeah. Okay. So now very, very useful results, which basically lay the foundation of the entire linear algebra. But it's better that all of us remember these results going forward. Okay, the matrix A in C to the m by n is said to be non-singular if and only if the null space of the matrix contains only one vector, namely zero vector itself. For example, if you substitute x equal to 0, A into 0 is definitely 0. Okay, so zero vector is always a part of null space for any A. For any matrix A, zero vector is a part of null space. Okay, but now what I'm saying here is only the zero vector should be in null space of A. Only then the matrix A can be non-singular. Okay, a matrix A is said to be non-singular if or only if null space of A equal to the set zero vector. It does not contain any non-zero vector in its set. Only zero vector should be in null space of A. Okay, this is very, very. In fact, today while describing some different cases of linear system of equations, we will use this fact very crucially. Okay. Now another aspect of null space of A is as follows. It's basically used to determine if a matrix is rank deficient or is it a full rank matrix. How? It's precisely given by the third relation. For any matrix A in C to the m by n, the rank of the matrix A plus the nullity of the matrix A equal to n, where n is nothing but the number of columns in A. Okay. Now we know what rank of A is. Last time we saw in depth some basic calculations and everything. But what is nullity? Nullity is really defined as the dimension of the null space of A. I think in the lectures, professor had mentioned about the basis of a vector space. The basis it essentially defines how many linearly independent vectors are there in a given space. What is the maximum number of linearly independent vectors? And what is that number? The number of such maximum independent vectors in the space is called the dimension of the space. So if I say dimension of null space of A, what I mean is I take the null space of A, I find out what is the maximum possible number of linearly independent vectors, and number of such maximum linearly independent vectors is called the dimension of the null space of A. And that is also cutely represented or called as the nullity of the matrix A. So this particular relation is also very famously called rank nullity theorem. Okay, it says that the rank of any matrix plus the nullity of that same matrix is always equal to the number of columns of the matrix A. Okay, so this is, for example, how to check whether rank is full or not. Just compute the nullity of the matrix A. Okay, if the nullity turns out to be, let's say, equal to 0, then rank of A is equal to number of columns, which means it's full rank. Okay, let me maybe write it down here. If nullity of A is equal to 0, that is 0 dimension. What does it mean to have 0 dimension? Means it has only zero vector. It does not have any other vector. You cannot find even one linearly independent vector in that space. Then it is rank or nullity of that matrix is 0. Then it's full rank matrix. If nullity of A is greater than 0, that is strictly greater than 0, strictly a positive number, then it's rank deficient. Okay, that is called rank nullity theorem. Now, fourth result says for any square matrix A, the determinant is 0. The determinant is 0 if or only if the null space other than the 0 vector, that is, you remove the 0 vector from the null space, the remaining space should not be equal to the null. That is, there should be at least one non-zero vector in the null space of A in order for the determinant to become 0. This is very simple. Why? Because if there is a non-zero vector in the null space of A, then the nullity of the matrix will be strictly greater than 1 or greater than 0. Then the rank will become deficient, which means determinant will become 0. Okay. In fact, this is one of the result of determinant. A matrix is said to be full rank. A square matrix is said to be full rank if and only if the determinant is strictly non-zero. Okay, so that is another result. Okay, we will now. So this is a brief summary of what professor had done in the class. So now what we will do is we will delve into the second part of today's session, which is part 2 on tutorials, some problems and corresponding solutions. Okay, so the first question is, compute the determinant of the matrix A equal to 1, 2, 1, minus 5, minus 1, 0, 2, 0, 2, 3, 3, 2, 1, minus 4, 4, 1. Okay, so it's a matrix in 4 cross 4 dimension. Okay, So this problem is really to get familiar with how to apply the formula that we have seen to compute the determinant of any matrix. Okay. So as an example, most often we only see 3 by 3, at most 3 by 3 matrices or 2 by 2 matrices. But now I'm going one step beyond by giving a 4 by 4 matrix and asking us to use the formula to compute the determinant. Okay. Solution. So we know that determinant of a matrix A is given by sum over J equal to 1 to 4 because M is equal to 4 and N equal to 4. 1 to 4, Aij, Cij for some I. Okay. Now let I equal to 1. That is IE expanding the determinant along first row. Then 2 j equal to 1 to 4, Aij, C, it's 1. 1 j equal to A11 C11 plus A12 C12 plus A13 C13 plus A14 C14. Now just substitute the values for A11, A12, A13 and A14, which is nothing but 1 minus 1, 2, 1, 1. That's nothing but C11 minus C12 plus 2C13 plus C14. Okay. So now how to compute C11? That's nothing but minus 1 power 1 plus 1 M11, which is equal to M11. Similarly, C12 minus 1 power 1 plus 2 M12 equal to minus M12. C13 minus 1 power 1 plus 3 M13 equal to M13. C14 minus 1 power 1 plus 4 M14 equal to minus M14. Okay, so then substitute these things in this equation. It implies det of A equal to M11 plus M12 plus 2M13 minus M14. This is equation 1. Let's compute M11. Okay, what is M11? Det after removing first row and first column. Okay, let's see that should be a 3 by 3 matrix, right? So basically what I'm saying is remove this row, sorry, the column, and remove this row. Okay, the remaining is this matrix. This is nothing but M11, this matrix, determinant of that matrix. You can show that that is given by 0, 2, 0, 0, 2, 0, 3, 3, 2, 3, 3, 2, minus 4, 4, 1, minus 4, 4, 1. Okay. Now this can be evaluated as 0 times 3 minus 8 minus 3 times 2 minus 0 minus 4 times 4 minus 0. It is nothing but minus 5 minus 6 minus 16. Oh, I'm sorry, this is 0. Okay, this is nothing but minus 22. Now M12, that is obtained by deleting the first M12, right? First row and second column, delete it. The remaining is this. Okay, this will become M12. So that is 2, 1 minus 5. 2, 1 minus 5. 3, 3, 2. Minus 4, 4, 1. Nothing but 2 times 3 minus 8 minus 3 times 1 plus 20 minus 4 times 2 plus 15. That is same as minus 10 minus 63 and minus 120 equals minus 193. Okay. Now similarly M13. Okay. M13 is basically obtained by deleting the first row and the third column. Okay, then you get 2, 1 minus 5, 2, 1 minus 5, 0, 2, 0, 0, 2, 0, and minus 4, 4, 1. Minus 4, 4, 1, which is nothing but 4 minus 40 equal to minus 36. Similarly, I'm just writing down the last determinant also, which is just obtained by deleting the first row and the last column, which is 2, 1 minus 5, 0, 2, 0, 3, 3, 2. This is nothing but 2 times 4 plus 3 times 10 equal to 38. Therefore, just substitute all the values. You get minus 22, minus 193, minus 72, minus 38, which will evaluate to minus 325. Therefore, determinant of A equal to minus 325. So I hope this was clear. So this is the procedure to compute the determinant of any n by n matrix. So I did it for told for 4 by 4. You can do the same thing for any n by n.
Hello, sir.
Yeah.
There is an error in calculation of M12. Minus not one M12. Last value it is not minus 120, minus 68.
So
4 into 17.
oh, okay.
Yeah.
So this is 17, right? So it is 268.
Minus 141.
Minus
141.
Okay, then here also. Then let's add up. So this will basically become 110, and this becomes 3, 6, 1. The total is 3, 9, 2.
273.
273. Correct. Yeah. Thanks for correcting it. Okay. So you can do this kind of approach for any n by n matrix. So here I did not demonstrate for 4 by 4. Okay. Now the next part question will be, we will look at some properties of determinants. Okay. So first property is if any two rows of A are equal, then determinant of A equal to 0. Okay. What do we mean? For example, if I have something like a 3 by 3 matrix, okay, determinant of a 3 by 3 matrix. Let's say A, B, C, A, B, C, E, F, G, right? So clearly the first two rows are equal. Okay, now what do I do is, so I want to expand the determinant. So let A equal to, let me expand it along the third row. Okay, A3J, C3J. That is, expand along third row. Basically, I set I equal to 3 instead of I equal to 1 in the last example. Then what is this? A31, C31 plus A32, C32 plus A33, C33. This is nothing but 3, 1 is E. E times. Okay, let me again maybe go through. You need to delete the third column and the first row. This one and this one delete. So remaining is, this is nothing but C31. Of course, there's a minor that is involved. Maybe I will do that also. Times minus 1 power 1 plus 3 into BC. Okay. Now this one will be plus A32 into, what is A32? F into minus 1 power 3 plus 2 into, then, so what I'm saying is this one and this one you should delete. Remaining is AC. Okay. AC. Then plus A33 is equal to G times minus 1 power 3 plus 3. This one will be AB. Okay. Now, this determinant is 0. This determinant is 0. This determinant is also 0. So total is 0. Okay. So if there are two rows of a matrix which are equal, the determinant is always 0. Second property, if A has a row or a column of zeros, then determinant of A equal to 0. That is, if it has any 0 row or 0 column, determinant is 0. Okay. Example. Let's say A, B, C, 0, 0, 0, D, E, F. Okay. And what you need to do is expand along second row. That is, expand along the column or row which has zeros. And what happens is 0 times minus 1 power 1 plus 2. I mean 2 plus 1, because that is the 2 plus 1 position, times M21. I'm not writing it because anyways it becomes 0. Again, you can show that 0 times, maybe I will write C22 plus 0 times C23, the whole is 0. Okay. Next, third property. If alpha is any scalar belongs to a complex field, then determinant of alpha A equal to alpha power n into determinant of alpha A. Okay. And A is a matrix in C to the n by n. What is n? N is this order, this dimension. Let me just give an example. Let n equal to 3. That is, I can take a 3 by 3 matrix. A equal to A, B, C, D, E, F, G, H. Now, alpha A is nothing but alpha A, alpha B, alpha C, alpha D, alpha E, alpha F, alpha G, alpha H, alpha I. Okay. Therefore, determinant of alpha A is nothing but, just take alpha A times alpha E, alpha F, alpha H, alpha I, minus alpha B times alpha D, alpha F, alpha G, alpha I, plus alpha C times alpha D, alpha E, alpha G, alpha H. Okay. Now, if you expand this, what do you get? Alpha A into alpha square EI minus alpha square FH, minus alpha B into alpha square DI minus alpha square FG, plus alpha C into alpha square DH minus alpha square EG. Okay. Now take alpha all common, it becomes alpha cube of A times EI minus FH minus B times DI minus FG plus C times DH minus EG. Now you can show that this is nothing but determinant of A itself. So what have we proved? Determinant of alpha A equal to alpha cube into determinant of A. But our n was equal to 3. Right? That's why 3 came. Therefore, in general, det of alpha A equals alpha power n into det of A. Okay, fine. Any doubts? If you have any doubts, please let me know. Okay. Now, there are some series of properties which I'm going to just state without any proofs or examples, which you can, but they will come really, really handy to understand further concepts in the course. The fourth property is, if A and B are two n by n square matrices, then determinant of AB, that is, you take the product of A and B and then compute the determinant, that is same as determinant of A into determinant of B. That is, you separately compute the determinant of A and B and then multiply them. This is same as determinant of BA. Okay, it's a very extraordinary property which you can use everywhere. I'm not giving example. You can always take an example. Take a matrix A, take a matrix B, multiply them and find determinant. Now take determinant of both the matrices separately and then product them. Now take the matrix B and then multiply it with A and then take the determinant. You can show that all these three values will be equal. Yeah, is there a question? Okay. Now, if fifth property is, if A belongs to C to the n by n, it's an n-dimensional matrix, then determinant of A transpose equal to determinant of A. That is, transposition of a matrix will not change the determinant of the matrix. Okay, that is the key that we need to remember. On the other hand, the following property is little interesting, that if A belongs to C to the n by n, then determinant of A Hermitian is equal to determinant of A and take the conjugate. Okay, just take the conjugate. It's going to be some scalar complex number. Take the complex conjugate of the number, that will become determinant of A Hermitian. Okay. Seventh property, swapping any two rows or columns changes the sign of determinant. Okay. Example. What I'm saying is, if A is equal to A11, A12, A13, and B equal to A21, A22. I'm sorry. The second row is A22, A21, A22, and A23, and third row is A31, A32, and A33. And what I do is I interchange R1 and R2. Let's say the first row and second row interchange to get the matrix B equal to A21, A22, A23, A11, A12, A13, A31, A32, A33. Okay. Then the property is that determinant of B equal to minus determinant of A. You can again check with an example. Next is the final property for this particular class. Subtracting a multiple of one row from another, or maybe I can write like this: one row or one column from another row or column leaves the determinant unchanged. Okay, the way to read this is subtracting a multiple of one row from another row leaves the determinant unchanged, or the other way is subtracting a multiple of one column from another column leaves the determinant unchanged. Okay, that's how you need to read this sentence. That is what I'm trying to say is, if let's say A equal to A, B, C, D, right, then determinant of A minus alpha C, B minus alpha D, C, D is same as determinant of A, B, C, D, same as determinant of A. Okay. What I'm trying to, so basically what did I do? I subtracted the second row, C and D, from the first row, A and B, by a same number, alpha C and alpha, by a same factor alpha. The subtraction of this one row from another row will not change the determinant, is the property. Okay, so I'll give you a small homework. Verify the above properties from 4 to 8 by taking examples. Okay, fine. Now the third question of the day. Let A belongs to C to the n by n, be an upper triangular matrix. Okay, then show that determinant of A equal to product of I equal to 1 to n AII. Okay, that is what I'm trying to say is the determinant of any upper triangular matrix is given by the product of the diagonal entries of the matrix A itself. That is determinant is the product of diagonal entries in A. Okay, so we will see a short proof along with an example. Okay, now let A equal to, it's an n by n matrix, right? So, and it's an upper triangular. What do you mean by upper triangular matrix? Okay, I'm writing down that particular structure. A11, A12, and so on till ANN. Sorry, 1n. A21, this will be 0. Then A2, sorry, 2. So on till A2n. Then 0, 0. A33, and so on till ANN. So all these things will be non-zero, some non-zero. So you see, what the structure of the matrix, right? All the entries above the main diagonal. Okay, so let me tell you. Okay, maybe I will mark it separately. So this is the diagonal of the matrix. Maybe I should remove this. Diagonal of A. So then this is called lower triangular, and this is called upper triangular. That is, all entries above the diagonal is called upper triangular, and all entries below the diagonal are called lower triangular. An upper triangular matrix is a matrix in which the lower triangular part is all completely zero, and upper triangular part is all completely some non-zero element. Similarly, a lower triangular matrix is some matrix where all the upper triangular parts are all zero and lower triangular parts are all non-zeros. Okay, so this is the definition of upper triangular and lower triangular matrices. Now the question is, for an upper triangular matrix, prove that the determinant of such matrix is equal to the product of diagonal entries. Okay, and I'm considering n by n square matrix. So define an, okay, like this: a11, a12, so on till a1n, 22, an, okay, 0, 0, 0. All these are zeros. Okay, these are all some non-zero entries. These are some non-zero entries. Okay. Now, how do I find? Okay. Now what I will do is very carefully see the last row contains only one non-zero element, which is namely that a and n. Others are all zero. Maybe I can highlight it again with some other color. Let me delete this. Okay, last row contain only one non-zero element. What you do is, the trick is as follows: expand along the last row. So what happens? You get all these are zeros, right? Only one non-zero element. So the determinant is nothing but a and n times minus 1 power n plus n times the minor of, okay, times m and n, the minor, which is nothing but a and n times minus 1 power 2n times a11, a22, and so on till a n minus 1 n minus 1. That is till this a n minus 1 n minus 1, the previous diagonal entry. Okay, again all these things are non-zeros. These things are zeros. Okay, now this guy is nothing but 1 itself, because minus 2 power n, 2n is nothing but an even number, so minus 1 per any even number is just 1 itself. This is nothing but a and n. If you recall, if I define this as an, means what does it mean? It contains n rows and n rows and n columns, with the first entry as a11 and last entry as a and n. And see this matrix, okay? Clearly see this. This contains n minus 1 rows and n minus 1 columns, again of the same form as this matrix. The difference is that there are now n minus 1 rows and n minus 1 columns. Can anyone tell me how to, call this matrix in terms of this representation as? If I call this as an, what is this called as? Can anyone tell me? Okay, so this is nothing but determinant of an minus 1. Because if I say an is containing n rows and n columns, with the first diagonal entries a11, last diagonal entries a and n of the form of upper triangular matrix, then an minus 1 should contain n minus 1 rows, n minus 1 columns. So the first element is a11, with the last diagonal element is an minus 1 n minus 1 of the form of an upper triangular matrix. Okay, so what do I have? Therefore, determinant of an, which is nothing but a itself, because that was my a. Determinant of a equal determinant of an, which is nothing but ann into determinant of an minus 1. Now, applying principles of mathematical induction, I can again similarly write an, determinant of an minus 1 to be an minus 1, an minus 1 times an minus 2. What I'm trying to say is, in order to evaluate the determinant of this matrix, again expand it along the last row of this matrix. You will then land up getting another sub matrix here. That will be an minus 2. Okay, this is like this. Okay, so similarly you can show, that means what? The an is nothing but ann into an minus 1 n minus 1 into determinant of an minus 2, which is nothing but ann minus 1 n minus 1 into an minus 2 n minus 2 into an minus 3. This is by mathematical induction, PMI, principles of mathematical induction. Okay, and if you keep on going, you can show that there's nothing but an n into an minus 1 n minus 1 and so on till a1, which is nothing but containing just one row and one column, which is nothing but a11, the first element itself. Nothing but product of I equal to 1 to n aii equal to determinant of p. Okay, I hope it was clear. Does anyone have any doubt? Okay, so I see no one has any doubt. So homework. Yeah, is there a question? Okay, so homework is prove that for an lower triangular matrix, A in C to the n by n, determinant of A is nothing but given by product of the diagonal entries. So be it upper triangular matrix or lower triangular matrix, both will have the property that its determinant is equal to the product of diagonal entries. Okay. Yeah, I see a question. The physical significance of determinant of matrix A. It's a very good question. So I will give you a hint on what that is. Okay. You can go and explore more, but I will give you the hint. So let's say I have a matrix A equal to A1, A2, and so on till AN. Okay, it's an n by n matrix. So each of these is a column vector. Okay, I'm writing the column vector notation of a matrix. Now what I do, let's in the Cartesian product system, let me find all the coordinates represented by each of these n vectors. Let's say A1 is this. Let's say A2 is this vector. A3 is this vector, and so on. Okay. Now the physical significance is that the parallelepiped formed by this, the parallelepiped formed by having these vectors as the sides of the parallelepiped, okay, has its volume equal to the determinant of the matrix A. Okay, you can note it down and you can go and check for more details. For example, in this case, it's something like a slant cuboid or 3D parallelepiped. Okay, and for example, if n equal to 3, so the determinant of a matrix A is basically represents the volume of the n-dimensional parallelepiped formed by the column vectors of the matrix A as the sides of the parallelepiped. Okay, det of A equal to volume of the okay. So I think Anupam, I think Mr. Anupam's query was this, and I just clarified. You can go and refer more about it. This is like one of the physical significances. The other question is from Mr. Akhilesh. We see the determinant of A is being used many places in signal processing, Any example, when do we use it and for what purpose? Yeah. So one very good example where we use determinant is basically to check whether a matrix is singular. If I want to solve, for example, this particular this particular very application of this MIMO wireless communications. If I want to find the receiver vector, a transmitter vector from the received equation. Suppose I know y, that is y is what I observe at the receiver, and h is a channel between the transmitter and receiver, which by some means let's assume that you know at the receiver. But x is the data that the transmitter wants to communicate with me, and I want to decode what the transmitter wants to communicate with me. So what I do, I just take the inverse of the matrix H and multiply with the y. Okay. So if you want to compute the inverse of the matrix H, if you go back and recall the definition of the inverse, you have a determinant there. So you need determinant to compute the inverse of any matrix. Okay. It in some sense refers to a singularity measure of any matrix. Okay. This is like a high level application, but in any kind of system, for example, even in electrical circuits, if you want to ultimately find the current in any nodes, you would want to invert it, and that basically requires determinant computation. Okay, so did I answer the question, Mr. Akhilesh? Yeah. Okay, thanks. So I think we are at 7:06 now. Okay, so I will give one last property and we will take a short 5-minute break and then resume after that. Okay, I'll just give a short property, which is like maybe property, very, very important property. Please remember this property, going forward surely without, forgetting it. If A is an n by n matrix, okay, determinant of A is equal to 0 if and only if rank of A equal to n, that is full rank. Okay, for any square matrix, the determinant is 0 if or only if the rank is sorry, not n. Okay, that is rank deficient. Only if the determinant is 0, the rank should be rank is deficient. On the other hand, if the rank is deficient, that is, it is not full rank, then necessarily the determinant has to be 0. Okay. So summarizing, full rank matrix is also same as saying that it's a non-singular matrix, which is also same as saying as determinant is non-zero. Similarly, rank deficient matrix is same as saying as singular matrix, same as saying as determinant is 0. Okay. Okay, so let me conclude at this point. I mean, the sense we'll take a short break for 5 minutes. Before we pause for now, there's a question that if it is not square matrix, how to find the determinant of A? So if you see the definition of determinant is defined only for square matrices. For non-square matrices, you cannot define determinant. So determinant is undefined for any non-square matrices. So for example, you're asking how to find determinant of inverse of a 2x3 matrix. Again, inverses are defined only for a square matrix. It's a good question. Inverse exists only for a square matrix, not for a non-square matrix. But there are some alternative, approximate inverses which are called a pseudo inverse for non-square matrices. But I think that requires little more fundamental development before introducing to a point of pseudo inverse. In fact, you raised a very good question here. For example, if you see this particular wireless receiver, it's not necessary that NT and NR has to be always same. It's possible that you may have, and so let's say this is a mobile phone, and let's say this is a base station, your cell phone tower. Your cell phone tower can contain as large as, for example, 64 antennas, but your mobile phone could contain only 4 antennas. In which case, this matrix NR is not equal to NT, in which case this is not a square matrix, right? So then how do we invert it? Yeah, that's a very valid question. In fact, that's also called, instead of doing this, they find something called pseudo inverse. Okay? If H is non-invertible, then find pseudo inverse of H. Okay, that has something else more. You basically do a kind of a projection operator. So I think Professor Jagannathan will, in some classes, will introduce the notion of least squares. Once he introduces that, then I will again take up that and explain the notion of what a pseudo inverse of a matrix is. Pseudo inverse is defined for any matrix, need not be square matrix, but the proper inverse which we are talking now is defined only for a square matrix. So maybe Mr. Anupam, you can pause on till, hold on till the point where least square is introduced, and then I can explain the notion of pseudo inverse. I think then it covers a larger umbrella. Okay, so let's stop now for about 5 minutes. Let's get back again at 7:15. Okay, so let's resume. Am I audible? Can anyone confirm if I'm audible? Okay, yeah, thanks. So we're going to study about in depth on all possibilities of this particular concept called system of linear equations. Okay, this is very, very important. In fact, one of the very, very useful applications of linear algebra in day-to-day life in terms of solving stuff for some unknown, for example, be it control systems where you want to basically find the optimal inputs that you want to. Those people who are familiar with control theory, they know that you need to give inputs, and then in order to lead these particular system into a stable state, and then it basically you can cast it as a system of linear equation where in every state you get to observe some observation, and depending on that you may want to solve for some optimal desired inputs at every state or something like that. So these system of linear equations are very important. So let's delve into it and take a deeper look at what are the various possibilities, how to solve different varieties of equations. For example, when the inverse is not defined, how the solutions will take form, and so on and so forth. Okay, so this is going to be a supplementary material to what professor had covered in the class. So let me just, for the sake of completeness, let me start with this particular statement that any system of linear equations can be expressed in matrix vector form. All right. So for example, you consider the following equations. Two x1 plus 2x2 plus 6x3 equal to 4. 2x1 plus x2 plus 7x3 equal to 6. And minus 2x1 minus 6x2 minus 7x3 equal to minus 1. Then you can basically represent this system can be written in matrix vector form as, okay, let me show this both together. 2, 2 minus 2, 2, 1 minus 6, 6, 7 minus 7 equal to 4, 6 minus 1. Okay. Oh, sorry. Let me move this. Times x1, x2, x3 equal to 4, 6 minus 1. So this is A. Okay. This is coefficient matrix. It's called as a coefficient matrix A. This is called the variable vector X. It's in C to the 3. A is C to the 3 by 3. And this is called the observation vector Y in C to the 3. Okay. That is, i.e., AX equal to B, or x equal to A inverse B. So this way you can find the solution, or you can find the unknown variables x1, x2, and x3. This is also unique solution because inverse is unique. Okay. The natural question is, what if A is not invertible? How to find solution? Okay, so let me give you the answer. In this case, either infinite solutions can exist, or no solution can exist. What do I mean by infinite solution? That is, you can find more than one vector x such that Ax equal to B is satisfied. What do you mean no solution exists? You cannot find even one vector x such that Ax equal to B is satisfied. Okay, we will look at these cases today. We will answer these in detail. I'm just giving you the answer, but we will look at, how is this possibility. The other related question is, what if A is a rectangular matrix? I think this was one of you had asked this, how to find inverse, right? Okay, because for a rectangular matrix, inverse is not defined, right? So basically, again, the answer is that if the matrix A is rectangular matrix, then if solution exists, right? If solution exists, then it cannot have a unique solution. See, if the inverse had existed, I know that the solution is unique. But if it's a rectangular matrix for which I don't have an inverse, and if I know that solution exists, how will I know if a solution exists? That we will see some rules later. But if at all the solution exists, then it cannot have a unique solution, but it will have infinitely many solutions. Okay, so these are very two important questions that it will be very clear at the end of this particular next 40 minutes or so. Okay, so please pay attention. Okay, so now let's delve into the possibilities. Okay, possibilities of solutions. So what are the possibility solutions for what? For x in Ax equal to B. Number one, no solution can exist. It's possible that you cannot find even one vector x such that Ax equal to B is satisfied. Such system of linear equation is called inconsistent system of linear equation. That is, you cannot find even one solution. Inconsistent system of linear equation. LE means linear equations. What is the other possibility? There's one unique solution. Okay. The third possibility is that not just one solution, it can contain infinitely many solutions. So these both cases are called consistent equation, consistent set of system of equation, because you can find solution, be it one or more than one. Okay, so now, so there are two categories, inconsistent versus consistent system. The first question is, when can a system be consistent and when is system inconsistent? Okay, now once we understand that when a system is consistent, then we will ask a question, when will system have unique solution, when will system have infinitely many solution? And after seeing all of these, we will take examples and then that will complete this particular module. Okay, so first thing that you will see is, when will solution exist, or when is a system consistent? Okay. For that, consider this particular equation, Ax equal to b. Okay. Now I can view this particular system of linear equation as follows. I can write it as set of column vectors an. Okay. For simplicity, consider consider A to be c to the m by n. Maybe I'll write it explicitly here. A c to the m by n. X is in c to the n. B is in c to the n by n. Sorry, n by 1. M by 1. M. Okay. And x I can write it as x1, x2, and so on till xn equal to b1, b2, and so on till bn. Okay, so each AI is c to the n by 1. Sorry, m by 1. Now this is nothing but, what is this? Nothing but saying x1 times a1 vector plus, note, x1, x2, and so on till xn are all individual scalars, but a1, a2, and a2, an are all vectors. So this is nothing but x1 a1 plus x2 a2 plus x3 a3 and so on till xn an equal to b vector. Okay. Therefore, finding a solution to x is same as asking, what is the question? What choices of x1, x2, and so on till xn should I choose so that the linear combination of a1, a2 to an with coefficients x1, x2, so on till xn gives vector b. Okay. Okay. So basically what I'm saying is, see, what this says is x1 a1 plus x2 a2 and so on till xn an equal to b. That means I'm asking for what choices of the coefficients x1, x2, and so on till xn will the linear combination of the ai's with the corresponding coefficients xi's will give the vector b. Okay, that is that is equivalent to saying that such xi's will exist, right, only if b, the vector b, lies in the column space of A. Correct? Because what is column space of A? You take all the vectors of column vectors of the matrix A and then do all possible linear combination of the matrix, these column vectors, and what all the possible resultant vectors is set to form the column space of the matrix A. Now I'm asking, if I want to find such xi's which satisfy the equation Ax equal to b, I'm asking what choices of xi's should I choose so that the linear combination will result in vector b. Or in other words, I can choose such xi's only if the vector b lies in the column space of A. Okay. So therefore, can anyone confirm if you're able to understand this? Or is this clear? Can anyone confirm? Yeah, example I will give you. Yeah, example I will give. But let me now state the rule, and then I'll give an example. That is the next thing I'll do. Therefore, a system of linear equations Ax equal to b is consistent if B lies in the column space of A and inconsistent if B does not lie in the column space of A. Okay. Okay. So example. I mean, yeah, I think it's a good time to give an example to ensure that um, we are on track. So let me take some example. So okay, maybe we will take the same example as what we took here. I have not tried it, but let's see. 2, 2, 6, 2, 1, 7, minus 2, minus 6, minus 7. X1, X2, X3 equal to 4, 6, minus 1. Let's come to the determinant of this. Let me check, just wait. 2 into minus 7 plus 13. Okay. Yeah. Okay. So what I'm saying is, okay, I mean, it's not very clear. Let me maybe give another example because this I need to solve for X and show you. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. X1, X2, X3. 8, 12, 15, and 18. Okay, suppose I want to solve for Ax equal to b, where A is given by this matrix and B is given by this matrix. Okay, you can maybe check that. Check this is nothing but x1 into 1, 2, 3 plus x2 into 4, 5, 6 plus x3 into 7, 8, 9 equal to 12, 15, 18. So basically I need to find for what values of x1, x2, and x3 will this be satisfied. Okay, you can just see that if x1 equal to x2 equal to x3 equal to 1, means I just add up all the column vectors. I will be able to get back my observation vector y, b, 12, 15, 18. Okay, that so basically then the solution is 1, 1, 1. You can verify the same thing. I mean, it's a homework. Maybe you can take it as homework by computing the inverse of the matrix A explicitly and multiplying by the vector b. You will get to be 1, 1, 1. Okay, so now what does it mean? You are able to make linear combination of all these three vectors, which are the column vectors of matrix A, with the appropriate coefficients 1, 1, 1, to get another vector B. But we know that such linear combination, this one particular linear combination of the column vectors of A, so the vector B lies in the column space of the matrix A. Or in other words, only if the vector B lies in the column space of matrix A, I can find some solution, that is some values of x1, x2, and x3 will exist. If the vector B does not lie in the column space of A, no matter what, I cannot find a solution for x1 and x2 and x3. So this is what I meant. Okay, I hope this gave you an intuitive picture of what I meant. Is it okay? Yes, this is a unique solution in this case. Now what I'm talking is whether a solution exists or not, whether consistent or inconsistent. I've still not categorized it into whether there's a unique solution or there's infinitely many solutions. So my claim is that a given system of linear equations is consistent. That is, you can find a solution only if the vector B lies in the column space of A. It is inconsistent. That is, there is no solution if vector B does not lie in the column space of A. This is the first thing that I want to tell. That is inconsistency versus consistency. Okay. Now let me tell when will unique. Basically, let me try to understand. Let me try to give you a theorem that will basically make this operational very clear. Okay, so it's called the Roche-Capellis theorem. Yeah, I think Mr. Anupam, you have told 1, 1, 1 is the only vector. Yes, indeed, because I've told A inverse B is equal to 1, 1, 1. So since A inverse is unique, B is also unique. The only vector that can satisfy is this 1, 1, 1. So it's indeed a unique solution. But my focus was rather to concentrate on the fact that I can find a solution only if the vector B lies in the column space of A. Okay. So now let's see this theorem. A system of linear equations with n variables has a solution if and only if the rank of its coefficient matrix A is equal to the rank of its augmented matrix A, B. Okay, what I'm trying to say is, if I have that is rank of A equal to rank of the matrix A concatenated with the column vector B. Okay, if this condition is satisfied, then the system of linear equations Ax equal to B will have a solution. Okay, that's so. I mean, it's intuitive because earlier I told that B should lie in the column space of A, which means B cannot be linearly independent of the column vectors of A. That is as simple as that, and this theorem is exactly saying that if you have the vectors A1, A2, and so on till AN, and the augmented matrix is A1, A2, and so on till AN, and the last vector is B. If B lies in the column space of all these vectors, column space of the matrix A, then B has to be a linear combination of these vectors from A1 through AN. That means B cannot be linearly independent of these vectors. So that means adding one extra column is not going to improve the rank, should not improve the rank. Because if B were not to be, if B has to be a linear combination of all these vectors, that means B is a linearly dependent vector on these columns, which means you cannot increase the rank by adding the vector B. That's where rank of A should be equal to rank of A augmented with the vector B. Okay, that is basically for the sake of completeness what this theorem says is the vector B cannot be linearly. Yeah, the comment by Anupam, that's correct. B is a linear combination of A1, A2, and so on to AN. That's why it has to be linearly dependent on these vectors. So the vector B cannot increase the rank. should not increase the rank. Yeah, that's correct. That is, a vector B cannot be linearly independent of columns of the matrix A for a solution to exist. This is because when B lies in the column space of A, for the system to be consistent, because for the system to be consistent, B should lie in the column space of A. B cannot be linearly independent of columns of A. Okay. Let's take an example now. Consider, maybe I'll take a different color. System of equations. X plus y plus 2z equals 3. X plus y plus z equal to 1. X 2x plus 2y plus 2z equal to 2. Okay. Now to check, is it consistent? Is the system of linear equation consistent? Okay. Solution. Okay. So what should we check? We should just check whether rank of A equal to rank of A augmented with the vector B. So rank of A equal to, okay, we'll first compute, maybe we'll divide it into 2 and then say rank of A. So A is nothing but 1 1 2 1 1 1 2 2 2. Okay. Now how to find the rank? As last session we saw that Gaussian elimination is the key. So what is the thing? So R2 implies R2 minus R1, which will give us 1 1 2 0 0 minus 1 2 2 2. Then R3 implies R3 minus 2R1, same as 1 1 2 0 0 minus 1 0 0 minus 2. Now R3 implies R3 minus 2R2, then you get 1 1 2, maybe it's plus or minus 0 minus 1 0 0 0. Right, so it's done. Then rank of A equal to, what is the rank of A? 2. Yeah, 2. Correct. Now let's compute rank of A augmented with B. So what is the matrix A augmented with B? 1 1 2 1 1 1 2 2 2 and 3 1 2. Okay, then same thing, maybe R2 implies R2 minus R1, that gives 1 1 2 3 0 0 minus 1 minus 2 0 0 minus 2 minus 4. Okay, then R3 implies R3 minus 2 R2, that gives 1 1 2 3 0 0 minus 1 minus 2 0 0 0 0. Okay, therefore rank of A augmented with B equal to 2. Okay, that means both are equal. So what is the solution? It is consistent. That means what? This particular system of linear equation does have a solution. But whether or not it'll have a unique solution or infinitely many solutions, we don't know. Okay. Maybe another example to say that for an inconsistent system of linear equations. Okay. Let's say x plus y plus 2z equal to 3, x plus y plus z equal to 1, 2x plus 2y plus 2z equal to 5. Okay. Then a is equal to 1, 1, 2, 1, 1, 1, 2, 2, 2. Okay. You can show that rank of A, but A augmented matrix with the vector B is 1, 1, 2, 1, 1, 1, 2, 2, 2, 3, 1, 5. You can show that rank of this matrix A augmented with B equal to 3. Therefore, not equal. Therefore, system is inconsistent. That is, no solution exists. Okay. Okay. So now we have found a way to ascertain whether a given system has a solution or not. Okay. Consistency versus inconsistency. Now, within consistency category, you have two more subcategory, whether it has a unique solution or infinite solution. So that is going to be the next rule that we are going to devise, namely unique solution versus infinite solutions. Okay. This is a result for a system of linear equations. Ax equal to b if the solution exists. Okay, that is, I'm saying consistent. Then the solution is number one, unique, if and only if null space of the matrix A equal to a zero vector. What does it mean? We saw that inverse will give a unique solution. Only if the matrix is invertible, you get a unique solution. But for it to be invertible, what should be the criterion? Determinant has to be non-zero. For it to be determinant non-zero, what should be the case? It should be a full rank matrix. So a matrix for which the rank is full, right, will have the in addition to that, okay, let me finish. Will only have unique solutions, but more than that, this particular condition should be satisfied. Rank of A equal to rank of A augmented with the vector B equal to number of columns of A. Okay. Now, this particular condition we already know. This is a test for consistency. But in addition, if this number is also happen to be equal to number of columns of A, then this will give unique solution. Okay. What is the intuition? Intuition is that now if null space of A is a zero vector, that means, what does it mean? It only means that it's a full rank matrix, not just that. The number of columns equal to the rank of the matrix. This is just by rank nullity theorem. Okay. So if the rank of A equal to rank of A augmented with vector B equal to number of columns of A, then the system is consistent with unique solution. On the other hand, the solution is not unique or infinitely many solutions, or maybe you can solution is not unique, or you can have infinitely many solutions if the null space of A apart from the zero vector is not a null, not an empty set. That is, you have at least one non-zero vector in the null space. That is, null space of A contains at least one non-zero vector. Or in other words, by rank nullity theorem, rank of A equal to rank of A augmented with B. This is for consistency, should be strictly less than number of columns, because if it has more than one non-zero vector, that means dimension, the nullity is strictly greater than 0, which means the rank should be strictly less than number of columns in A. Okay. Now let's go to that. Let's now see some example. Take the previous example. Okay. That is this particular example, right? This example. This one where we saw consistent system. A equal to 1, 1, 2, 1, 1, 1, 2, 2, 2, and B equal to 3, 1, 2. Okay, we clearly saw that B lies in the column space of A. Okay, that's where we got rank of A equal to rank of A augmented with B. But what did we see? We saw that rank of A equal to rank of A augmented with B equal to 2. We saw that's what we saw here, right? We saw rank of A is equal to rank of A augmented with B is equal to 2. But that is strictly less than 3, which is equal to number of columns in A. That means this system contains infinitely many solutions. Okay, great. Okay, so now what we have seen until now is we have seen a test to whether a system is a consistent or inconsistent solution. If a system is inconsistent, nothing to worry, because we don't have any solutions, so there's no progression in that stage. But if a system is consistent, then we saw a test to ascertain whether that is having a unique solution or that has an infinitely many solution, namely using this particular condition whether rank is less than number of columns or rank is equal to number of columns. Now, after having ascertained that, we need to now understand how to find the solutions. Okay, that is going to be the last part of this particular session. I'll be wrapping up this within 10 minutes, even less than within 10 minutes. Okay, the last part is how to compute the unique solution and how to compute the infinite solutions for a system. To a consistent system of equations. Okay, so if AX equal to B, unique solution exists if rank of A equal to rank of A augmented B equal to number of columns. In this case, null space of A equal to just zero vector implies det of A is not zero, determinant is not zero, implies A inverse exists. Therefore, the unique solution is X equal to A inverse B. Okay, this is a unique solution. Now, next thing is very interesting: how to compute infinite solutions. Okay. Now we saw that in this particular case, clearly rank of A should be less than number of columns. Okay. Therefore, null space of A apart from the zero vector is not equal to empty set, which means determinant has to be 0. This is what we saw in the last property before starting with system of linear equations, which means A inverse doesn't exist. So x equal to A inverse B cannot be the solution. You need to do something else. Okay. So now I'm giving you the solution, X solution. That is the solution to this consistent system, which has infinitely many solutions, is given by two components. It's called XP plus XF. Okay, where XP is the particular solution obtained by putting zeros at the position corresponding to non-pivot columns. I'll explain by an example what I mean by this. Then and XF is a vector in null space of A. Okay. Now let me give an example and explain. What do I mean by this? Let AX equal to B with A equal to same, there's this particular example I'm taking where I claim that it's inconsistent, right? 3, 1, 2. Oh, this the same example because I told infinitely many solution. The consistent with infinitely many solution. So I'm going to take the same example and I'll find the solution for this. Okay, 1, 1, 2, 1, 1, 1, 2, 2, 2, and B equal to 3, 1, 2. Clearly, we saw that it has infinitely many solutions. Okay. Now, first step 1, do Gaussian elimination of A. So what do you get? 1, 1, 2, 1, 1, 2, 2, 1, 2. R2 implies R2 minus R1. You get 1, 1, 2, 0, 0, minus 1, 2, 2, 2. And R3 implies R3 minus 2 R1. You get 1, 0, 0, 1, 0, 0, 2 minus 1 minus 2. And finally, R3 implies R3 minus 2 R2. You get 1, 1, 2, 0, 0, minus 1, 0, 0, minus 2. Right? Now, what is non-pivot column? Non-pivot columns are basically the columns in which non-zero pivot column. Oops, what happened? Non-zero pivot columns are the columns in which there is a pivot, a proper pivot. Okay. So, for example, this particular row has a pivot here, which is the third column, right? But this first row has a pivot in the first column. So this is a this is a pivot column. Okay. Similarly, this is a pivot column. But this is a non-pivot column. Okay. This is a non-pivot column. So that means the second column is non-pivot, right? So then what you do? Second column is non-pivot column. Therefore, put x2 equal to 0. Okay, then find x1 and x3 such that, I mean, the original system of linear equation, A, I'm writing A into, instead of x, I'm writing x1, 0, x3, because the second column was pivot, non-pivot column. So put a 0 in the non-pivot position, equal to 3, 1, 2. Okay. Now what is this? Nothing but x1 into 1, 1, 2 plus x3 into 2, 1, 2 equal to 3, 1, 2. So, I mean, you can just, now what you can do is, write this as x1 plus 2x3 equal to 3, x1 plus x3 equal to 1, 2x1 plus 2x3 equal to 2. If you solve this, you will get x1 equal to -1 and x3 equal to 2. Therefore, your x particular, xp is equal to, your x1 is what? -1, x2 is 0, x3 is 2. Okay. Actually, it looks like a mechanical procedure now, but as and when you understand better about null space and so on and so forth, you will know why this particular solution methodology is the correct method. Okay. For now, just take it on faith. Now we found xp. What about xf? It belongs to null space of A, right? How to find null space of A? Very simple. Just ax equal to 0. Find 1x. That's enough. So 1, 1, 2, 1, 1, 2, 2, 1, 2 into x of 1, x of 2, x of 3 equal to 0 vector, because that's the definition of a null space vector. You can show that one such vector which satisfies this particular equation xf is nothing but 1, -1, 0. Okay, therefore x solution is given by, okay, there's a small correction here. It's not just xf, it is any c times xf where c belongs to any complex number. That's because if xf belongs to null space, any scaled version will also belong to null space, because after all, they're all subspaces, right? So then xsol is nothing but xp, which is nothing but xp is nothing but the -1, 0, 2 plus some c times some scalar times 1, -1, 0. So this is the solution. Now, how is it infinitely many solution? Because the c variable can take any value. It belongs to, c belongs to any complex number, any real number or any complex number. So for every choice of c, you get one x solution. So that's why, since there are infinitely many c's you can find, so the number of solutions is infinitely many. Okay, let's have a quick check. Okay, whether this is correct solution or not. Check. Okay, let's solve a into x solve. Nothing but a into xp plus a into cxf. Nothing but a into xp plus c into axf. But since xf is null space, he will go to 0. This is same as a into xp, right? This is nothing but 1, 1, 2, 1, 1, 1, 2, 1, 2 times a particular solution is -1, 0, 2. You can show that this will give to 3, 1, 2, which is same as your B. Okay, so this is how you find the solution to system of linear equations when the system has infinitely many solutions. Okay, are there any questions? Okay, so if not, this is the end of today's session. So then we will meet next week. So yeah, if there are any questions, are there any questions again? Okay, so if there are no more questions, then we can stop for today. Then